All right, let's jump right into this explainer for lesson 2.7. Today we're unpacking the fundamental differences between chemical compounds and physical mixtures. Have you ever wondered why some things can be easily pulled apart while others seem perfectly, permanently locked together into something entirely new? Well, we're going to look closely at the very building blocks of the material world around us. We'll be doing a bit of scientific detective work to decode exactly how matter interacts, and we'll back up the theory with some really fantastic visual evidence to make it all crystal clear.
So, here's a quick roadmap of what we're covering. First, defining compounds and mixtures. Then, we'll dive into the classic iron-sulfur experiment, break down the scientific meaning of the word pure, and finally, apply all of this to everyday mixtures like the air and water around us.
Starting right off with Section 1, defining compounds and mixtures. We really need to draw a hard line between these two concepts. Understanding this distinction is absolutely crucial to making sense of everything that follows.
Okay, so the absolute crux of it is this. Are the elements chemically bonded to create something brand new, or are they literally just sitting next to each other keeping their original identities? When atoms of elements bond tightly together to form a compound, the properties of that new compound are completely different from the original elements it was made from. It's a total transformation. On the flip side, in a mixture, different substances share the same space, but they aren't bonded. They haven't changed chemically at all, and they keep all their original individual properties.
To make this super tangible, let's look at two totally distinct elements out in the real world. First, we have sulfur. It's a non-metal element that's bright yellow, very brittle, doesn't conduct heat or electricity, and is definitely not magnetic. Now, contrast that with iron. Iron is a metal. It's hard, gray, super strong, conducts heat and electricity wonderfully, and is highly magnetic. Keep those distinct properties in your head because we're going to put them to the test.
Moving right along to Section 2, the iron-sulfur experiment. This is where it gets fun because we actually get to see these definitions play out in a step-by-step lab scenario.
Imagine taking some of those gray iron filings, dumping in some yellow powdered sulfur into a beaker, and just giving it a really good stir. What we've created right there is a physical mixture. It's incredibly straightforward.
And honestly, this brilliantly illustrates a mixture. Because if you were to scoop it up and look closely, you can clearly see that zero chemical change has occurred. You still see the distinct specks of yellow and gray. The iron is still iron, the sulfur is still sulfur. They are just sharing space.
Now, because their individual properties haven't changed, separating them is a total breeze. Remember how we said iron is highly magnetic? Well, you can simply run a magnet over this pile of powder, and it will pull all the gray iron filings right back out, leaving only the yellow sulfur behind. It is literally that easy.
But let's kick things up a notch. We take that exact same mixture, drop it into a boiling tube, and blast it with intense heat from a Bunsen burner. We heat it up strongly until the mixture actually starts to glow, and then we pull the heat away and let it cool down.
That glowing, that is the visual proof of a massive reaction taking place. By adding extreme heat, we are forcing the iron and sulfur to chemically combine, fundamentally altering what's inside that tube.
If we zoom way into the particle level, we can visualize exactly what happened. The individual yellow sulfur atoms and the orange-gray iron atoms that were previously just casually sitting next to each other are now, thanks to all that heat energy, tightly bonding together. They pair up to form a brand new compound, which we call iron sulfide.
And now for the ultimate test. Grab that same magnet we used earlier to separate the mixture. If you try to hold that magnet against the glass tube containing our new iron sulfide, absolutely nothing happens. The iron can't be separated anymore. This proves without a doubt that the original elements have lost their original properties to create something totally new. The iron sulfide isn't magnetic, and it doesn't conduct electricity. It is a genuine compound.
Let's move to Section 3, the scientific meaning of pure. With those definitions locked in, let's tackle a word that gets thrown around all the time in everyday life, usually incorrectly. People love using the word pure, especially in marketing, but scientists view this word very, very differently. In a lab setting, the word pure is incredibly strict. It describes a substance that contains exactly one single kind of matter, with absolutely zero other substances mixed in. For example, scientifically pure water contains only H2O molecules, and literally nothing else. If it has even a microscopic trace of something else mixed in, any scientist will tell you it's a mixture, plain and simple.
Which brings us nicely to Section 4, everyday mixtures, air and water. Keeping that super strict, unbending definition of pure in mind, let's examine two things we interact with constantly. I think you'll find the reality is a lot messier and honestly, a lot more interesting than you might expect.
Take a deep breath. When we look at the composition of the air around us, it is clearly a massive mixture of different elements and compounds. It is definitely not a single pure gas. The air you're breathing right now is roughly 78% nitrogen and 21% oxygen. That remaining 1%, it's a total grab bag of carbon dioxide, argon, water vapor, and small quantities of other gases.
And what's wild is that air is a highly dynamic mixture. The exact composition isn't some static recipe, it constantly changes. For instance, the amount of water vapor shifts depending on the weather. Carbon dioxide levels fluctuate naturally because of plants and animals respiring, but also heavily due to human activity, like burning fossil fuels, which pumps excess carbon dioxide into our atmospheric mixture.
At a microscopic level, you can picture this perfectly. All these different molecules, the oxygen, the nitrogen, the carbon dioxide, they just bounce around freely, together in a shared space. But crucially, just like our iron filings in sulfur powder before we heated them, these gases aren't chemically bonded to one another. It is a textbook physical mixture.
Okay, prepare to feel a little bit cheated by marketing next time you hit the grocery store. You see the word pure plastered all over bottled water, right? Well, scientifically speaking, not marketing is entirely false.
Seriously, just turn the bottle around and look closely at the typical analysis label. You'll see a long list of completely different substances. Now, these aren't impurities in a bad way. They are natural minerals that have dissolved directly into the liquid water as it flowed through the earth.
So, far from being scientifically pure, a standard liter of drinking water is a rich mixture. It can contain about half a gram of dissolved minerals like calcium, magnesium, potassium, sodium, and chloride. Because these minerals are just dissolved into the water and they aren't chemically bonded to the actual H2O molecules, the water remains a mixture.
And we can prove this. Just like we separated the iron from the sulfur with a simple magnet, we can separate the water from the minerals. If you were to boil that mineral water in an evaporating basin over a Bunsen burner until all the liquid turned to gas and evaporated away, you would actually see the mixture's solid mineral components left behind as a dry residue. It's a simple physical separation for a physical mixture.
So, as we wrap up this explainer for Lesson 2.7, I really want you to start looking at the world around you with a scientist's eye. Think about the desk you are sitting at, the drink in your hand, or the air filling your room. Ask yourself, what is truly scientifically pure? What is a complex, chemically bonded compound? And what is just a clever physical mixture just waiting for the right tool to pull it apart? Thanks for joining me on this deep dive into the material world, and keep questioning what everything is truly made of.